has a Poisson lambda distribution, then the variance of x is also lambda. Hey, pretty great, right? The mean and the variance of a Poisson lambda are both lambda. Okay, so that should be pretty easy to remember. All right, so let's prove this. First of all, I'm going to use that inside-outside formula. The variance of x for any random variable we know is the expected value of x squared minus the expected value of x quantity squared. So begin with expected value of x squared, right? We already know the mean is lambda, right? So I can just come back and slap that on the end and get the variance. Right now I need to get the second moment. Remember, that's what this is called, the second moment. Okay, so I'm just going to begin like we did when we proved the mean, except this time, remember, we've got a function of a random variable, and that's the squared function there. So I'm going to do like so, weighted against the probability mass function. K squared, and let's see, this will be e to the negative lambda times lambda to the k over k factorial, right? And then let's see, what can I do? I guess I could pull out an e to the negative lambda and a lambda, right? This is constant, so I'll definitely pull out. I'm also going to pull out a lambda because, I don't know, that's what I did when I proved the mean, so maybe I could do it here too. And also note that that first term is 0, so I'll just go ahead and change the index to start it at 1 there. K squared, lambda to the k minus 1 over k factorial. All right. And let's see. Oh, I can cancel one of these k's with the k that's down here. That'll be lambda e to the negative lambda. I'm just kind of feeling my way here, folks. This is some of these are moves that they just look like things that we can try, right? Things that we've done before, even k times lambda to the k minus 1 all over k minus 1 factorial. Okay, let's see, what could we do now? Maybe at this point, maybe I could make another change of index, like we did in that last problem. Note that the first term over here is it really begins with having a 0 factorial in the bottom, because when k is 1, then 1 minus 1 is 0 factorial, and this will also be a 0. So maybe I'll just make a change of index like that. J equals 0. Here, j equals k minus 1, okay? So j will go from 0 to infinity, and then what do I have there? Lambda to the j over j factorial, but then this k must, remember, if j is k minus 1, k is j plus 1. All right. So what could I do with that? Hey, look, I could probably just split this summation now. I could have two sums now. See? Watch this. I'm going to move up here now. So all of this is going to become lambda e to the negative lambda times the sum. J goes from 0 to infinity. I'm going to have two sums. Okay. First one is just going to be j times lambda to the j over j factorial. Second sum is going to be j from 0 to infinity of 1 times lambda to the j over j factorial. See how I did that? So I had that j plus 1 factor down there. All right, lambda e to the negative lambda times, what is all this stuff? Well, you know what? If you look closely, you'll see that this is really j minus 1 factorial, right? So this is lambda to the j over j factorial. This is, you know what? Actually, all this is just lambda e to the lambda. All of this whole sum is just lambda e to the lambda. Okay, I can pull a lambda out there, and you'll see that that's indeed the case. So all of this is just this is just e to the lambda. Okay, so this just becomes lambda e to the lambda plus e to the lambda. And that turns out to be lambda e to the negative lambda times lambda e to the lambda plus lambda e to the negative lambda e to the lambda, right? And so the whole thing just becomes lambda squared plus lambda, okay? So finally, we can come back and finish off the variance of x. The variance of x then, it's going to be expected value of x squared minus the expected value of x quantity squared, which is lambda squared plus lambda minus, remember, the expected value of x is lambda. So I'm going to square that, and it's just lambda. Awesome.